Good morning, students. Today we are here to discuss the second chapter of your chemistry book of class 10th, acids, bases and salts. It's a very important chapter and a little long one. We will discuss it in detail. Maybe at least 3 or 4 classes will be needed, I think. So from the beginning, be very serious about it. In the previous chapter, we had learned about chemical reactions and equations. We learned about what is a chemical change and what is a chemical reaction. We discussed that chemical change is such a change in which new substances are created. New substances with new properties. That's why it is different from a physical change. Suppose ice melts into water, they look different, but there is no new properties, new substances, because in the chemical construction, ice and water are the same. So that is not a chemical change. But hydrogen gas and oxygen gas, they combine to a certain proportion and create water. That is a new substance with new property. And that is a chemical change. So chemical change is the change, such a kind of change in which new properties, new substances with new properties are created. And what is a chemical reaction? Of course, chemical reaction is the process by which a chemical change occurs. That means a process by which new substances with new properties are created. We call that a chemical reaction. The properties that combine, that react, we call them reactants. And the new substance with new properties, we call them products. And we must remember, in a chemical changes, chemical reaction, through a chemical reaction, new substances with new properties are created, but never a new atom is created. So the total mass and the total charge of the reactants will be the same as the total mass and net charge of the products. Only new molecules are formed through a chemical change. Let's look at a few slides to recap this portion, and then we will go to the actual study matter of today. Well, so far so good. Let's talk about these new substances that are compounds. These compounds, elements are limited, compounds are infinite. Like you know, in any language, the number of letters alphabet are limited. In English only 26 letters. But by combining, we produce crores of words, new words. And the digits 0 to 9, only 10 digits in mathematics. But we combine them and make almost infinity number of numbers. In the same way, although we have a limited number of elements in the nature, in the world, and some are man-made also, but we combine, chemically react them together. Nature does, and also human beings also do it to produce millions, trillions, infinite number of compounds. But there are 3 basic ways of producing this compound. You understand that. Number 1, say compounds may be created in 3 ways. First one, say we combine we take one element and we combine it in a certain ratio, certain proportion. You have studied about the law of proportion that you studied in class 9. And we produce a compound. That is one way of producing a compound. Let's take an example. Sulfur. Sulfur is an element, and also take oxygen. You know that sulfur has this valence is 6, oxygen 2. If we cross over this, you have learned in class 9, cross them over and also cancel. So now we have SO3. The structure, molecular structure will be like this. Now you see, this is a compound that is made up of one element and the second element. They make up a compound which we call sulfur trioxide. Now for a moment, let us say we add to this structure another oxygen atom. Now there are one sulfur and 4 oxygens. So you see, 2 oxygens are in double bond, that's alright. But these 2 oxygens are in single bond, so they have 1 electron left. So now this term becomes SO4, a sulfate, but an ion. Are 2 anions, sulfate 2 anion. So this will become a new compound. Again we combine the same 2 elements, but it becomes a new compound. So in this way, element plus element, when we mix them according to different proportions, they produce newer compounds. Right? Now, we can also combine a compound. So this compound is the 4, which is an anion with another element to produce another compound. A compound combining with an element to produce another compound. Say, we take this SO4, which has valence 2, we have seen it, and we combine it with hydrogen, which is an element which has valence of 1. We cross them over. And so what we get is that H2 and SO4. So we combine it and get H2 SO4, a new compound which is made up of a compound and an element. That is the second way a compound is created. Right. Now come to the third way. That is obvious, you can understand it by now. That now if we take one compound, say this one, H2SO4, and combine it with another compound, say sodium hydroxide, NaOH, and that also produce another compound, and not only one, that will produce 2 compounds in fact. You remember this neutralization reaction from your previous chapter. The moment these 2 things come together, the sulfate and the sodium, they get separated from the hydrogen and the hydroxide ion. What happens in case of 4? Separated it again have 2 ions, 2 valences, and sodium will have 1 valence. They combine by crossing over, so now it becomes sodium sulfate, Na2SO4. So Na2SO4, so we must have balance in this way also. But what happens to this H2 and that 2OH, they combine into 1. So here we see compound and compound. They together make sometimes new compounds. In these 3 ways, in nature, countless number of compounds are being created. We also create such compounds every day for defined purposes in our laboratories. So, you see, to trace all kinds of compounds in this world, the world is made up of such countless, infinite number of compounds. We must study them properly. And so, to study something properly, which is many in numbers, we have to classify them. We must classify. Why do we classify anything? When there are too many in numbers, to learn about them separately and make proper use of them, proper use of the properties, we classify things. So compounds are so many in number, we must classify them. One easy way of classification is very simple, according to the sources. According to the sources, compounds, like many other things, they can be classified as organic. That comes from the plants, animals. Even in our body there are certain compounds. And inorganic. Inorganic here means from the minerals, that is also from the nature. And also sometimes we synthesize compounds in the laboratory. So that is another way of doing it, natural and man-made. But you see, there are so many kinds of compounds that this simple classification does not apply, does not tell us about the properties, about the chemical properties of each category, even remotely. So we make a new category of classification. And that classification are acids, bases and salts. What are acids, bases and salts? All the compounds in the world, according to their chemical properties, we classify them in 3 categories. And these 3 categories are acids, bases and salts. Elements can be acidic, elements can be basic, but only compounds can be acids, bases or salts. Mixtures can be acidic, basic, even has a properties of a salt, but acid, bases and salts are the classification of the compounds. Here you just go through the slides a little more and then we go into further about the properties of each.
Natural and man-made elements. They are limited in number. But the compounds that are made of those elements, combine those elements and also other ways, are countless in number. They also can be man-made or natural. They can be found in 3 ways: by combining an element with an element, by combining a compound and an element, and also by combining a compound and another compound. Look at the figures, equations carefully. Now, to know the properties of such a huge number of compounds, you can understand what countless number of compounds must be there. And why know them? Because to put them to more efficient use in our daily life, to benefit from the use of the compounds, we must categorize all compounds according to their chemical properties. And that is in three groups: acids, bases, and salts. All the compounds of this world, they, according to their chemical properties, are grouped as acids, bases, and salts.
In fact, throughout the ages, even from prehistory, when history was not written, human beings have always tried to classify everything in its surroundings: living, non-living, plants, animals, etc. etc. So we also, throughout the ages, we tried to classify acids, bases, and salts, when even we did not know what a scientific laboratory was. How? We primarily classified them by taste. In fact, acidus, this word means sour taste. Base has bitter taste. You yourself have learned this in class 4th, 5th level. But what is an acid? Acid is something that tastes sour. Base, what is base is something that tastes bitter. What is salt? Salt is, of course, it's what is tasting salty. But you are now a little adult, grown up a little. Now you, of course, understand that childhood description will not do. Because you cannot go on testing everything in the world without knowing its properties. It is very dangerous for us that we don't know what this thing is and we are going to test it. No. It's, of course, you understand that is foolish. So we must in the laboratory have some other way, surefire way, that will not endanger ourselves in any way without putting it into mouth or onto a screen. Some other way to know whether this is an acid or this is a base or this is a salt. To do that, we use a thing called indicators. Indicators. What is an indicator? What does an indicator do? An indicator indicates. Indicator indicates whether a particular compound, a particular substance is acidic or basic, whether it is an acid or base. It points, it shows. It can do it in two ways. An indicator can indicate visually. It can be a visual indicator. What does visual indicators do? They change color. They change color. If you put a visual indicator in acid, it will take one color. If you put it in the basic solution, it will take another. And another kind of indicator will be here, which we call olfactory. This is a new word. Olfactory is pertaining to smell. Some indicators are there which give a different smell. It changes odor or smell. In acid, it gives certain smell, and in base, it may be giving some others. And that way, indicators may be both, natural and man-made. When we say olfactory indicator, what is indicator? Indicator is something that points out by visually changing color or changing the odor whether a certain substance is acid or base. Say olfactory, natural indicator. Onion. Onion you have seen at your home. It has a very pungent smell in it. Now if you take some onion, raw onion, the smell is there, and you soak it into a soap water, which is a basic solution. In the soap water, you soak the onion for a few minutes and then try to smell it again after washing it with the water to wash away the soapy smell. Now the natural smell of the onion will be good. So it indicates that the soap water was basic. In the same way, vanilla. You know that vanilla, you must have eaten also vanilla ice cream, vanilla cake. Vanilla is a fragrance, an aroma that is taken from an extract from a certain plant product, vanilla. Now this vanilla has a smell of its own. You know that's a very sweet smell. This smell also goes when it is put in contact with some basic solutions. So these are natural olfactory indicators. But as you see that these are not very dependent because they don't change odor when they are put into acid. They only change odor in the base. But we must be sure that more sure way of knowing whether this is acid and this one is base. So visual indicators are more in use in the laboratories. Let us talk about them. But first, let us give you a slide about these indicators, the definition. Please learn all these definitions I am giving you 2 slides because they will be part of your question answer in the CBSE examples.
An indicator is a substance that points out whether a certain substance is basic or acidic in nature by either changing color, that will be a visual indicator, or by changing its own smell, which will be an olfactory indicator.
If you take natural visual indicator, let us take another very common substance from your mother's kitchen, your home kitchen, that is turmeric. Haldi. You make a paste of turmeric and put some soap water, mix it with soap water. It will be reddish brown. It will change color into a reddish brown color. Sometimes you have seen that if you have by mistake, by accident, put some dog or on your shirt and made it a yellowish color, and then you try to wash it with soap water so that your mommy doesn't know, you will see that the yellowish color will not, actually the color will not go, it will only change, it will become reddish brown. So turmeric is another natural indicator, visual indicator, to tell us what is acid and what is base. But it is also again not dependable because it does not prove what is acidic or not. It only is base. And such other natural indicators are like the petals, colorful petals of say China rose, Gurhal, and hydrangea, xeranium. These are some of the colorful petals of flowers that also are natural visual indicators. But again, they are not very dependent because they either give you the tell you whether it is acid or whether it is base, but never both separately. Most important, most dependable, most visual natural indicator is litmus. This name you have learned even from your 4th or 5th standard, that litmus, in acid, it changes into red, in base it changes back into blue. Now, this is the most important natural visual indicator we have in this world. What is a litmus? Litmus is a symbiotic organism. You know symbiotic organism. When two organisms live together to help each other survive, we call that relation symbiotic. And here this litmus is the extract taken from an organism called lichen. It is naturally purple in color, but of course when it is put into acid, it turns red, and when in base, it turns blue. Let's learn about a few things about this lichen and litmus by a slide. Please look at it.
A few naturally occurring olfactory indicators are onion, vanilla. A few naturally occurring visual indicators are turmeric. Also petals of flowers like China rose, hydrangea, petunia. Red cabbage juice is also a natural visual indicator. But the most commonly used natural and visual, also most effective indicator is litmus. It is purple in natural color, but when in acids turn litmus solution red and bases turn litmus solution purple. Litmus is an extract taken from a symbiotic organism. We call it lichen. A combination of a alga called Rocella tinctoria. It belongs to the thallophyta group of plants and a parasitic fungus. They live together. We extract this litmus, essence of the litmus solution from this organism.
And just because most of the easily available litmus is not very easily available unless we do it synthetically, produce it synthetically in the laboratory. We cannot depend on all the experiments we have to do in the laboratory these days, only on natural indicators. So we have produced many synthetic, man-made, laboratory indicators which are more dependable to signify whether this is an acid or base. One of them is methyl orange. Now this, you see its color, obvious color, that it is orange. In acid, it becomes red, and in base, it becomes here. Another one is phenolphthalein. Notice the spelling carefully. PHENOL, Now this is a chemical which is colorless. Colorless in acid, it remains colorless. But in base, it becomes pink. This is another man-made visual indicator. But in a proper laboratory, we say it in the laboratory, different kinds of acid and different kinds of bases. This universal indicator is the most dependent for laboratory work. Because you see, universal indicator does not only indicate what is an acid and what is an base, but it also tells you, it changes color 14 times. It also tells you how strong an acid is or how weak, and also how strong a base is and also how weak. We will discuss it in a little more detail when we will be discussing about the strength, how an acid can be strong and how a base can be strong or weak. We will discuss the pH factor of acidic and basic solution. At that time we will detail about this universal indicator a little more. But for the time, these all are preliminary ideas about acids, bases, salts, how to recognize it. But most important is, we must know the chemical properties of acids and bases by way of knowing their way they function and how we can best make use of it. We are going into that. Before that, let's have a slide to recap all these things we have learned up to now.
The universal indicator is the most efficient one, both in our daily life and for subtle scientific experiments. A universal indicator, you see the picture, not only points out an acid or if it is a base, but it also shows how strong or weak that acid or base is on a 14-point pH scale. You look at it carefully. At 0, it is the strongest acid, and as you move towards 14, it becomes less acidic. At 7, neutral point, that is distilled water, it turns green. It is equally acidic and equally basic if you ask that neutral. And then its acidity goes lesser and lesser and basicity increases. And at 14, that is the darkest blue, it is most basic. If you want, you can go through and remember this chart. It is best to see in the laboratory, do that. But at this point, just remember that distilled water, it is the purest form of water. It is 7 in pH scale and green. And below that, water also becomes slightly acidic. And above that, water also becomes slightly basic. Now, let's go to the next point.
Now, let us get into the proper business. What is an acid and what is a base? Again, just as in class 4th you learned a little about acid and base, and now you know that that knowledge was very much insufficient. At class 10th level, you will learn about a little more about acid and bases, but what we are going to learn in class 10, that definition of acids and bases in their aqueous solution. What is an aqueous solution? An aqueous solution is such a solution in which the solvent is aqua, water, a water solution. So what we are going to learn now are that theory given by this man, Arrhenius. Arrhenius acids, Arrhenius bases. Acids and bases in their aqueous solution. That is all we have to learn in class 10. In the upper classes we have more elaborate theories of acids and bases, but in class 11, 10th, we learned about the Arrhenius theory. This man Arrhenius is not very important in your syllabus because to know about the scientist is not important. It is important to know about their work. Just as in the literature classes I tell you that it is not very important to know how the poets and authors lived their life. It is more important to know what message they have left in their works. But as well to interest you that this a little unknown name Arrhenius is not so unknown in the actual world of science. You can look up in the net about him, you will find that his country name have named one mountain after him. That is not a very easy everyday thing that a mountain is named after a certain scientist. And also a crater on the moon is named after him. The scientific world really reveres this man. But what we are going to discuss about now is the Arrhenius theory of acids and bases. What does Arrhenius tell about acids? An Arrhenius acid is a substance that in its aqueous solution, it gives out a H plus ion, a H plus ion, a substance that when it is mixed with water, it dissociates. It dissociates, we can say it scientifically, it ionises and gives out at least one H plus ion. And what is an Arrhenius base? An Arrhenius base is such a substance that when mixed with water or in its aqueous solution, it dissociates and gives out a OH minus ion. We call this ion a hydroxyl ion. H plus ion and hydroxyl ion, the substances in their aqueous solution, when they produce more hydrogen ion, H plus ion, we call them acid. And when they produce more hydroxy, OH minus ion, we call them basic or base. Now let's first look at these two definitions to occur, and then we will explain what do we actually mean by this H plus and OH minus. Mind you, I again remind you that these are Arrhenius acids and bases. There are other theories which include substances in their not only aqueous solutions but in solutions, other solutions like some substances that are soluble only in alcohol, some substances that are soluble in ammonia solution. How to define them as acid and base? We have other theories about these, like say Bronsted and Lowry theory of acids and bases. Or we have Lewis acids and bases, etc. We will not learn in detail about this theory in this class. You are not. You don't need it, and you need a little more knowledge about the elements and compounds before learning them. But we will touch them a little in the next video, so that this theory of Arrhenius theory that you have to learn in this class will be a little more clarified. But first look at the slides about the definition, the theory occurs. Please look.
According to Arrhenius theory, an acid is a substance which, in its aqueous solution, dissociates, or we can say ionises, to give out H plus ions. An acid which is completely ionized in water is a strong acid, and the one which is only partially ionized is a weak acid. H2SO4, HCl, hydrochloric acid, HNO3, that is nitric acid, are some of the strong acids. And according to Arrhenius theory, a base is a substance which in its aqueous solution dissociates, or we may say ionizes, to give out hydroxyl OH anion minus ions. The base which is completely ionized in water is a strong one, and which is only partially ionized is a weak one. Potassium hydroxide, calcium hydroxide, magnesium hydroxide are some strong bases. You see, the bases which are soluble in water, they are usually very strong bases, and water soluble bases have a special name. We call them alkali, but we will talk about it later on.
Since we have very little time left for this period, we will go into the detail of these theories in the next period, along with the other bits of other theories to clarify even more. But let's solve one question that is arising in your mind, that why do we have to learn only about Arrhenius theory? Because the drawback of the Arrhenius theory is obvious from the definition we have given, that it is applicable only to the aqueous solution unless some particular substance is soluble in water. How do we know that it is acid or base through this theory? That is absolutely correct. That is the main shortcoming of the Arrhenius theory of acids and bases, and that's why we need the other theories. But we have to learn to start step by step. We learn about the aqueous solutions first, because you know, in our everyday natural surroundings, most of the acids and bases we find, like say hydrochloric acid that is in our stomach, or the say organic acid like the acetic acid, oxalic acid, all these naturally occurring acid bases that we use in daily life like soap, they are mostly water soluble and in their aqueous solution. So we start with this aqueous solution, aqueous soluble acids and bases, and that's why Arrhenius theory is first. We touch the other theories also a little, but you learn the definition very well.
The main shortcomings, faults, drawbacks of Arrhenius theory. Number one, they are applicable only to the compound soluble in water. Unless the compound is soluble in water, how can we know whether it is acid and base? But there are compounds which are not soluble in water and base. We will give you an example of that. Second point, they do not give us a clue to the nature of substances which has hydrogen in them, but that hydrogen is not dissociable. Like alcohol, like glucose, they also have hydrogen in them. We don't know, they are also water soluble, but they are not acid according to Arrhenius. We will also give an example for that. And the third point is that since it takes water as the main solvent, so it does not clarify about the nature of the water itself. And we will learn in the upper classes that water is amphoteric in nature. It shows both basic and both acidic characteristics. Such substances that show both acidic and basic characteristics are called amphoteric. Let us look at the examples of these faults. Here is an example where you see that water in which hydrochloric acid solution has been given. It is acid, so the hydrochloric acid H is dissociable. But in the second picture we have glucose solution where C6H12 pol 6. There are 12 hydrogen atoms, but they are not dissociable. So when we connect a battery and a bulb in the water solution, the bulb glows because it has become acidic and because the hydrogen has dissociated. But it is not an acidic solution where the glucose, it is soluble in water, but it has no dissociable hydrogen. So the bulb does not glow here. Arrhenius acids, one of the shortcomings is this one. Now the second experiment you have seen that if we mix strong sulfuric acid in a hot tube that concentrated sulfuric acid on some sodium chloride, what will happen is that HCl gas, HCl not solution, HCl gas will be produced. You see in the second picture how through a rubber cork and a glass pipe HCl gas is passed. Now this is gas and has no water in it. It is not in the aqueous solution. Now if you put a dry blue litmus paper in that HCl gas, there will not be a change of color because it is not in the aqueous solution. But the moment you soak the blue litmus paper a little in water and put it before the HCl gas, it will turn red because now it is in connection with the water molecules in the litmus paper. So this is the second fault where we don't see that unless a substance has water in it, it does not show acidic or basic nature. Now the third point is that we have already maintained that water also can be of acidic and basic in nature. On pH scale number 7 neutral point, that is only distilled water. Distilled water has equal amount of hydrogen ion and hydroxyl ions. When we don't drink distilled water, you have remember it. We put it in the battery, we put it in the injection when we give injections, but we never drink it directly. And water, when the pH scale comes down from 7, it becomes acidic. And when it moves over 7, it becomes acidic. Arrhenius theory does not explain this amphoteric nature of the solvent. It explains only the nature of the solute, not the solvent. And yet we must learn Arrhenius theory in the beginning because all these water-soluble acids and bases, the aqueous solutions, are the most common in everyday use of our life, both in organic and inorganic forms. That's why at this level, class 10th level, we will touch the other theories also, but we must start and understand the Arrhenius theory very well. It is the base, fundamental. So be very careful to learn the basics.
And one more thing I am giving you extra for today, just to think it over, and you are quite adult now, you can go through the nets and other books to be a little prepared. That is, the key to the factor of knowing an acid and base according to the Arrhenius theory. An H plus ion and an OH minus hydroxyl. You see, you can look up the class 9 syllabus about this ion, what is ion atom once more. But what is an H plus ion? You see that H, hydrogen, is a unique element. It has 3 naturally naturally occurring isotopes where the atomic number is the same but mass number is different, because the number of proton is always 1, that makes it hydrogen, but the number of neutrons in this case is different. So the valence is also different. So you see, the moment I say H plus ion, we are talking of 3 naturally occurring isotopes of hydrogen. There are actually 7 isotopes of hydrogen, but the rest 4 are man-made, H4 to H7. What we are talking about, protein. Protein, that is H, only element in nature that has the same mass number and the same atomic number. That means it does not have a neutron atom. This is the 99 almost % of hydrogen found in the nature. So we are mainly dealing with protein. It is so much in all the hydrogen atoms. But let's also learn about the other two. Deuterium. Its mass number is 2, so it has 1 proton and 1 neutron. And another is tritium. These two are very least in amount in the available hydrogen, 99% is protein, so we are talking about protein. And one more thing I was telling you, that hydrogen is especially unique. Perhaps this is the only element that has different names for its isotopes. Other isotopes we usually do not have separate names. Anyway, let's see at this protein. Protein has 1 proton, that is plus 1 charge in the nucleus, no neutron. And so naturally it has only the K orbit, K cell, in which to make it has 1 electron to make it an atom. It needs 2 so that the outer orbit, the K cell, is complete. And take the ionic structure, it takes 1 more electron, it becomes minus 1 anion. That is the structure of helium. But how it becomes a plus ion? If it gives or shares this outer electron, either it shares with somebody else or it gives it up for some reason. What remains? Now it is H plus ion, H cation, not anion. But what it is? It is simply a proton. What is a H plus ion? H plus ion is the proton in its simplest, original form. It's a proton. Now, this H plus proton, when it gets separated from some acid, say we take some water, lots of water molecules are there, and there H2O, and we put HCl inside this. What is HCl? H and 1, Cl has balance in 1, they cross over to make a HCl. So when this HCl goes into this H2O molecules, they dissociate and gives H plus, which is a proton, and Cl minus, because it is a non-metal. It will produce an anion. Leave it for the time being. Look at these H plus protons that are floating around into H2O. Now what is H2O? What does this proton does when they are alone and in search of another electron, another molecule, whatever, the opposite charge, just to be stable. That is the point we are going to start our next period from. So please be ready when you come in the next period with all these definitions. Look it up a little more at W plus 9 syllabus about ions and etc. ionic compounds, and we will give you a detailed study about this Arrhenius theory, the structure of acid bases, etc. Till then, stay strong, stay safe, stay home, study hard, and of course come back with proper homework. Right? Thank you.